Hello everyone, this is Dr. E, and for today we're going to be working on parallel and perpendicular lines in geometry. In algebra, we know that slope lines have the same slope, and perpendicular lines, one of their slopes would be the negative reciprocal of that particular line. And for today, we're going to be using theorems, postulates in parallel and perpendicular lines to answer some problems in geometry. So let's start with the parallel postulates. And in this postulates, it says here that through a point not on a line, there is one and only one line parallel to that given line. And this is the illustration for this parallel postulates, which is a lot easier to understand if we have a visual. So let's say we have two parallel lines, and this line is line L that is parallel to this line right here. We know that there's only one point in this parallel line, or one point in this line that would have a parallel line to L, because if there is another line, let's say this is line S, and if there is another line that is intersecting P, let's say line M, this line M is no longer perpendicular to L because there's only one line, which is line S, that will be parallel to this line L right here. And this is the parallel postulates that we're going to be using in our problems later on. And if we have parallel line postulate, we also have the perpendicular postulates. And in this case, through a point not on a line, there is one and only one line perpendicular to the given line, which is quite similar to what we have shown on the parallel line. So if this point P right here, we cannot have another line that will cross or intersect point P that will give you a perpendicular line to L. So this, or these two, are our postulates that we're going to be using so that we'll be able to understand our theorem. And the next theorem is that the perpendicular transversal theorem that states in a plane, let two parallel lines be cut by a transversal. If the transversal is perpendicular to one of the parallel lines, then it is perpendicular to the other parallel lines. Which means if we have, so this theorem, perpendicular transversal theorem, it simply states that if we have line M and line L, and they are parallel to each other. If we have a line intersecting M and L, and this line, let's say line L right here, I mean, we already have line L here. So let's say this is line N. This line right here that is perpendicular to line M, consequently, is also perpendicular to line L. So this is basically what the perpendicular transversal theorem states. So if L is parallel to M and T is perpendicular to L, then T is also perpendicular to M. So this is this theorem on perpendicular line, which we can also apply similarly to parallel lines. So two lines parallel to a third line, we have a theorem that states if two lines are parallel to the same line, then all three lines are parallel to each other. So we're seeing three lines that are parallel to each other, which means, let's say we have 1, 2, 3, A, B, C. Let's say A is parallel to B. If A is parallel to B, then if we have B also parallel to C, so that means A is also parallel to C. So all these three lines would be parallel to each other using this parallel, or two lines parallel to a third line theorem. So if we have A that is parallel to B and B is parallel to C, then we know that A is also parallel to C. So this is kind of like the transversal theorem for perpendicular lines, but this time it's going to be for parallel lines. So now that we have all these theorems, we can now write our first two-column proof by proving that T is perpendicular to M, given that parallel lines LM We have a transversal T, and one of them, just one of them, is given or known to be perpendicular to T, and that is L. So the first thing that we're going to be doing is, of course, just like what we always say when we are working with two-column proof, it's always easy to draw our figure. So in this case, we know that this is line L, and this is line M, and this is the transversal T. We also know that this angle 1 is a right angle because it's given, and this is just angle 2, and we know that L is parallel to M because it's also given. So since we have given statements, so let's write our statement and our reason for each of the statement to prove that T is parallel to M. So the first statement is, of course, the given statement, and we know for statement 1 that L is parallel to M and T is perpendicular to L. And we know that because it's given. And from here, we can now say that since we have two angles here, 1 and 2, using angle 1 and angle 2, we are seeing two familiar angles and familiar form, and they are corresponding. So when they are corresponding, we know that they are congruent. So we can state that angle 1 is the same or congruent to angle 2, and we know this because of the corresponding angle converse. So this is our second statement. And for our third statement, since we know that they are congruent and 1 is a right angle, therefore 2 should also be a right angle because they have the same measurement, because they are congruent. So we can use that as a statement, and that's our third statement, wherein angle 2 is a right angle. And we know that because of the definition of right angles. And since we have established that we have two right angles for angle 1 and angle 2, and we know that L is perpendicular to T, then we're able to solve now or prove that M is also perpendicular to T, which we're going to write here. And we know that because of the definition of perpendicular lines. And we have now shown our proof for this particular problem. And again, my handwriting is a little bit ugly, so let's have a recap and let's give you a better writing in the screen right here. So first, we started with the given information, and we know that L and M are parallel, and we have a transversal that is perpendicular to L, which is T. We know this because it's given, and we also know that angle 1 and angle 2 are corresponding, and when they are corresponding, they are congruent, so we can also write it down for our second statement. 1 is congruent to 2 because of the corresponding angles converse, and when they are congruent, they have the same measurement. So if angle 1 is 90 degrees, we know that angle 2 is also 90 degrees or a right angle because of the definition of the right angles. And we know that in perpendicular lines, the right angle is very important, and we have seen that two angles are formed as a right angle. So we know now that T is perpendicular to M from this statement. So now that the definition of perpendicular lines prove that T is perpendicular to M, we're finished with our two-column proof. So this is how we use our theorems in answering problems similar to this one. So let's continue and work on some theorems on perpendicular lines. So the first one is that if two lines are perpendicular, then they intersect to form four right angles. So that means if we have perpendicular lines, this is our perpendicular lines, they form 1, 2, 3, 4 right angles. So all this quadrant right here, they are all 90 degrees, 90 degrees, 90 degrees, and 90 degrees. And the sum of this is equal to, not 180, 360 degrees. So this is the perpendicular lines theorem. So if L is perpendicular to M, we know that we will form four 90-degree angles using this theorem. So angle 1, angle 2, angle 3, and angle 4 are all 90 degrees. And the perpendicular lines theorem the second perpendicular lines theorem that we're going to be using is that if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular to each other. And what we're seeing here are words like linear pair and congruent angles. And linear pair, they're equal to 180 degrees, and congruent angles, they have the same measurement. And when this happens, the lines are perpendicular. So if we have two intersecting lines, they form two angles, angle 1 and angle 2, and angle 1 and angle 2 are congruent, and when they are congruent, they form a linear pair because of this 180 degrees right here. So that means if these two are congruent, we also form two right angles. Therefore, we know that these two lines are perpendicular. So this is the second theorem on perpendicular lines. If we have line L perpendicular to M, they form linear pairs that are also congruent. Therefore, L is perpendicular to M. So let's start working and using those theorems to answer this problem, wherein we're going to be solving for x. And we know that when we are solving for x in a geometry problem, we need to combine our skills on algebra and geometry to be able to find the value of x. And to be able to do that, just like proving, it's always easy if we visualize our figures. So we know that this is N and this is L, and we know that these lines form a 90-degree angle. So that means measurement of angle 1 is equal to 90 degrees. From the given diagram that we are seeing, we also see two rays, one here and one here. This is 49 degrees, and this is y degrees. This is 63 degrees, and this is x degrees. And from this problem, we're looking for the value of x, and the value of x here is associated with this complementary angles right here, because we know using the theorem that we had a while ago that if we have one 90-degree angle and they are intersecting, we are also forming four 90-degree angles. So that means we can now use algebra to form an equation, because we know that N is perpendicular to L, and from here our equation will be 63 degrees plus x degrees is equal to 90 degrees. And we're able to formulate this equation because of the theorem. And now we can use algebra to find the values of x, or value of x. So we subtract 90 and 63. So x is equal to 27 degrees. And this is how we use geometry and algebra to solve problems similar to this one. And we're able to do that because we know that line N, the vertical line, form a 90-degree angle because they are given. And from here, we know that angle 1 is 90 degrees and N is perpendicular to L because we only need one perpendicular line, one 90-degree angle in two intersecting lines to know that we are forming a perpendicular line relationship. And from this theorem, we're able to construct our equation because now we're certain that N is perpendicular to L. So 63 plus x degrees is equal to 90 degrees is the equation we're able to formulate from this theorem. And using algebra, we found that x is equal to 27 degrees. And this is how we use algebra and geometry in answering problem like this one. So your number bender challenge of the day: find the measurement of angle 5 given this diagram and comment it down below, and let's see how you're going to explain your work on how you found Angle 5 using the theorems that we have from this lesson. So in geometry, we know that postulates, theorems, these are important because sometimes we need to formulate our own equation to solve for a math problems in geometry, and to be able to do that, we need to combine our skill in algebra and geometry to solve problems like what we did today. So practice is essential if you really want to gain confidence in answering complex problems like what we just did today. This is Dr. E, and see you again next time. Bye!